Thank you very much for your kind support, and please forgive us, myself and Dr. Jha, because we are meeting after a very long time, so we could not hold ourselves, so we made it a bit personal. So, but anyway, so day two post lunch session. In the session, we would have one presentation by Dr. Abhishek Jha from Gdańsk University, Poland. And after that, we have arranged the participants networking. It's optional. Whomsoever is interested, they can enter. There would be 3 rooms. I'll talk more about that later. But to start with, let me introduce our former students. Dr. Engineer Abhishek Kumar Jha before you. And it's a pleasure to have one of our former students in this course. Dr. Engineer Jha is a Bachelor of Engineering in Electronics and Communication Engineering with honors in 2009 from the University of Bardhaman, and M.Tech in Microwaves and Electronics Engineering with Microwaves major in 2011 with distinction from this university. And he got his PhD degree with major in RF and microwave from IIT Kanpur in 2017. He was then associated with Institute of Photonics and Electronics, Prague, as a postdoctoral research fellow. Since 2018, he is working as the assistant professor in Department of Microwave and Antenna Engineering at Gdańsk University of Technology, Poland, if I pronouncing it properly. Okay. And he has authored or co-authored more than 50 articles in reputed journals. He holds one patent on metamaterial-based planar microwave sensors. His technical articles have been cited more than 500 times with a very high H index of 12. His current research interests include analysis and design of novel microwave circuits and components, development of RF and microwave sensors for non-destructive testing, and measurements of intrinsic and physical properties. Dr. Jha, we all know that Dr. Jha is instrumental in IEEE activities. He founded and chaired IEEE MTTS SBC at Kanpur in 2014. He was the chair of the oral session of IEEE CAMA 2014 in France and joined the IEEE Volt program in 2018. He is currently serving as the associate editor for 2 leading IEEE journals, IEEE Access and IEEE Sensors, and is a potential reviewer of IEEE transactions or industrial electronics and IEEE transactions or microwave theory and techniques, IEEE transactions on instrumentation and measurement, and Nature Scientific Reports. We are happy that he has received several awards: Microwave Graduate Fellowship Awards in 2015, IEEE Site Design Awards in 2015, University Gold Medals for BE and MTech degrees in the University of Bardhaman, the Gandhian Young Technological Innovation Award in 2016. He is the recipient of several international travel grants, including the Young Scientist Travel Grant from the DST Government of India in 2016. He was awarded IDUB Premium Award from the rector of the Gdańsk University of Technology, Poland this year. So with that, I introduce Dr. Engineer Abhishek Kumar Jha. His talk title would be Electromagnetic Sensing, Waveguide Techniques. I repeat, Electromagnetic Sensing, Waveguide Techniques. And now I request Dr. Engineer Jha to start his presentation. Dr. Jha, the floor is yours.
Okay. So first of all, very, very thank you, my teacher, Dr. Bose, for presenting me well on behalf of this very well organized faculty development program. And I wish all success to this program. I hope the participant will enjoy today my presentation. As you said, I was very happy to accept this opportunity to talk with all my listeners today or viewers today through my alma mater organized program. And I'm very happy to present some of the technical research articles or research subjects which I carried out. So I hope you will enjoy. And can you all see the slides now? I just want to verify.
No, till now, no, we cannot see your slides. I think you have to do once again.
Okay, so I have to do start sharing. So I hope right now you can see. Is it now visible?
Still now, no. I think it takes some time. I'm once again making you presenter.
Yes, I shared the slides. I
Mhm,
hope it's.
mhm. Last time it was okay. This is
Mhm.
the problem with this.
Okay. I hope now it should be.
Yes,
So there were.
yes, yes. You are visible. Please continue.
Okay, so thank you. So without much delay, I will just start the today topic, electromagnetic sensing, waveguide techniques. I am Abhishek Kumarja from Dansk University. The G is silent in this pronunciation. And I want to just let you know that where I am from, I'm talking from. I'm from, of course, India, from Burdwan University. I did MTech, but where I'm now, I just want to tell you that this is Poland in Central Europe, and the Dansk University has quite old heritage. It shares the old heritage established by Germans in 1904, almost completing 116 years. So it has approximately 41 field of study. UG students are 18,000. Professors are more than 1,300. I hope now it is 1,400. Employees and PG students also you can see it's quite rich. And the below two pictures you can see how it looks like in the warm season, like in summer. If you come here in June or July, you will see the very lush green campus. And when you will arrive here late after October, maybe in the December and January and February, you will experience a very nice snowfall. So I don't want to delay the technical stuff. So I will let you know the outline of presentation will follow this trend. It would not be strictly following, but I have prepared as such that I will just introduce very popular sensors and their applications. And then I will try to introduce some radio frequency sensors, some electromagnetic sensing techniques I will talk about, just a brief of what I'm going to talk and why. So introduction will tell that all. And the recent works at the where I am working, Polytechnica Gdansk, that will also be carried out, but I have taken it in the last. So it is just to maintain the continuity. So I will mainly talking about electromagnetic sensing of materials, and I will try to focus on waveguide technique, because as I promised to deliver the lecture on waveguide techniques, and especially I will introduce Epsilon near zero sensing. So we will see how and why we need this waveguide and what we can measure through the waveguide techniques. And lastly, I will conclude the session. So it's a very simple sensors available in the market, and we know the sensors are very common to our daily life. So those sensors, what you are now seeing on the screen, are either mechanical or chemical or electrical sensors. So the principles are different, but the reading or the sensing, after sensing, the processing data should be meaningful, and it should be advantageous for different applications. So that is the meaning of real sensing. Otherwise, nature has also given us a lot of sensors. So as we know that, now I'm coming to the frequency sensor, because today I will talk about the frequency related sensing techniques. So some frequency sensors which is very natural, and we use it on our common daily life. It is like we all heard about Rene and Weber test. So a tuning fork which is resonating at 512 hertz is vibrated by the doctor, and then it is passed across the ear or on the head, touched on the head, to just observe how the patient replies through their experience. And when the conduction, bone conduction is greater than air conduction, then the doctor say, okay, you have a hearing loss. Okay, and if air conduction is greater than the bone conduction, it is all based on the hearing capability of the patient. Doctors say that, okay, this is the primary test and very efficient, you can do in minutes. So what is the process? Process is the source, which is tuning fork, should vibrate in the range of detector. So human ear is the detector, and we all know the range of the human ear, right? And what is the processor? Processor is our human brain, because we experience it, we hear it, then patient try to say the doctor, and doctor say, okay, so based on your experience, I know that you have problem. So okay, it's the similar condition we can measure. We all know, I think, in the intermediate of science education, we all do this experiment. It's very common experiment where a tuning fork again resonate in the column filled by the water, half water, and we can measure the sound, speed of sound, or the depth of the water level. So these are the sensing technique based on very common sensors like ear, or our eyes. So suppose we all have our skin and eyes also act as like a sensor, and they all behave at different frequency. They can sense what I want to target here, that each of the sensor has its specific application and can sense based on their characteristic. So our skin can sense infrared. It sounds very unusual maybe, but it is true that we can sense the temperature from coming from the sunlight, right? So when we are under the sunlight, we observe some warmth, we experience warmth, and that is due to the infrared signal in the terahertz to, I mean, gigahertz to terahertz. You can see that the wavelength is 700 nanometer to 1 nanometer is the infrared wavelength, and similarly the eye. So we can only see the visible spectra that lies on 390 nanometer to 700 nanometer. So each sensor, the natural sensor that nature provides us, also has some limitation and the characteristic. So the talk now will be diverted to a little bit more focused, not diverted, a little bit more focused. So what we want to listen today, it is why we need the microwave sensors, like electromagnetic sensors. Electromagnetic has wide spectrum, but now I'm converging to the microwave, because we know low frequency we have detectors like our cardiogram, or our cardiogram tell that, okay, what is the heartbeat rate and what is the problem in the valve. So it can be detected by ECG. Yeah, right. And that is called like classical electrophysiology, that also can probe inside the mind and can say, okay, the neurons or it is functioning well or not. So those all happen in like 5 hertz or 10 hertz, like that frequency. Very high frequency, we can detect, okay, this is firefly, and our eyes can see in the night. But what in the in the mid frequency, RF and microwave frequency, we don't have a certain kind of ready devices. So we need to analyze, and we need to target that what we want to focus. So basically, all the mediums, when we say medium in RF and microwave, medium is defined by its property. It has property of dielectric constant, magnetic constant, their losses, and the propagation constant. So if we know this, we can define any medium, right? We can know about the medium properties, and we can know about how electromagnetic wave in the RF and microwave frequency can experience and react if it is propagating through that medium. So sensing through RF and microwave is basically knowing about the property of those materials, mediums, we say medium. So some conventional RF sensors we all know, like a diode detector that detect the modulating waves envelope. We can detect again the power sensor, which has I think the inverse square law followed by this power sensor give the power of the microwave signal. So the car key finder we all know, and everyone I think all aware about the slotted line sensor that senses the electric field standing wave of the inside the waveguide. So we tune it, we propagate the we take the sensor, and we check where the maxima and minima is inside the waveguide, and we can characterize the wave inside the waveguide. So it can give out us the standing wave ratio rho, the wavelength of the wave, I mean the guided wavelength. Of course, we know that the guided wavelength is different than the free space wavelength. So we can know the guided wavelength, we can know the gamma is reflection coefficient, the amplitude we can know the impedance of the line, we can know the admittance of the line. So this is a very, very known experiment in microwave, and we can say that these are the sensors, right? Sensors are giving you meaningful data at the end after processing, and these are the microwave sensors. So these are conventional RF sensors. Some radio frequency sensors that are also common in market, and they are quite advanced, and they work in different principles, mostly in the wireless kind of sensors. So you can see like the tactical sensor where you can find the enemy targets while handling from the handheld device. The chip card like a Google Pay card or our bank card, they are also having RFID chips, and the signal can be transmitted in near field. The radar speed gun works on the principle of radar, and transmitting and receiving signals can be detected, and the time and delay can give the speed according to the Doppler effect we all know. Okay, so like, and the RFID is also implanted everywhere. If you go in shopping mall, library, everywhere, these sensors are now a common integral part of our daily life. So we cannot go we cannot leave them. Okay, we are adopting it very very welcoming to the microwave sensors. These sensors work on radio frequency detections kind of technology, and where still what I represented earlier, that there is a sensing part, then and maybe it could be the antenna, or it could be any device, transmission line, it could be a horn antenna, it could be a the simplest antenna what you can consider, like a patch antenna, or it can be very, very large array of antennas, or like a radar. So these principles are common, detecting and sensing, and how we do it, how we process it. Processing is a really different task that depends on the which kind of algorithm you choose, what you want to detect. So then our process changes. And finally, the result. So this three combination is always there in any type of microwave and RF sensors. So I will again come to the point that why we want to do this. So microwave sensing or electromagnetic sensing in RF and microwave, why it is needed? It is needed due to the it has a lot of application. The advantages are huge. It can say what kind of material it is. It can give the features of the material, like which kind of geometry it is. If it is a plane, if it is a automobile, or what kind of plane it is, it also gives signature. So I'm talking broad sense here, but we will slowly converge it to the waveguide technique. I'm still don't want to divert from a very small problem today we will discuss. So I just wanted to tell the viewers that okay, the electromagnetic sensing has huge application. So this is that's why it is now is a high topic in research areas. Electromagnetic sensing techniques. How many techniques are there to characterize material? I will focus today on characterizing the material. So sensing is quite a broad subject still, we all agree. So I will try to converge now on electromagnetic sensing technique of materials. So there are mostly handful of techniques, okay? So you can say more concisely, you can say two types. Maybe it's transmission reflection or it is resonant. So transmission reflection means you have a signal which goes, which leaves the transmitter, and then whatever the reflected signal comes back, depending on the signature of that reflected signal and knowing what was the transmitting signal, we can detect, we can characterize the material. Okay. And the second, which is resonant technique, that gives okay, what is the change in the frequency, resonant frequency, of course, and the quality factor of that resonance. So these two parameters of resonant technique give you the material characteristic. So it has all demerit and merits of the techniques, as always every techniques has. So we will find out, but we will try to discuss at least one of each the technique, and I will try to my job here is to give you the problem. I mean, what is the problem now in this area, and what is going on in this area, on the state of art of this area. So I will try to just give a brief of what is the problem we are, if we want to take this as a research field. So what is the problem is still open problem, and what people are giving the solution. So you can also propose your solution, so it is free. So suppose this is a coaxial line, okay, the top picture and the left side picture, and the right side is a waveguide. So both you can consider as a transmission line, and each of the transmission line has a sample of length d, and this sample is unknown to us, okay, and we need to characterize it. When characterizing means we need to get the electrical parameter in terms of epsilon, which is dielectric constant, magnetic constant, I mean the permittivity and permeability. I think it's a well-known term, okay. So if we try to write the equations, I hope that the audience is quite well aware of the scattering parameters, reflection coefficient, transmission coefficients, uh, the the propagation constant, and every impedances, and they know all basics of this microwave. So if we formulate, if we try to write the equations, transmission line equations, so we can know that how the transmission parameter or reflection parameter can be written in terms of the reflection coefficient and transmission coefficient. I mean, if it is T is the suppose the transmission phase factor, which depend on the phase of the material, I mean the gamma propagation constant. If it is lossy, then alpha will also be there. But if it is the not lossy, low lossy or lossless, then alpha can be neglected. So this can be written in terms of S21 also. Okay, S21 is the transmission coefficient. So and this is quite old. You can see it is if I remember, it's 1974. In Nicholson, Weir Ross, three scientists proposed this idea in 1974, and they formulated this, try to give the closed form equation of this transmission reflection parameter in terms of the material properties. But if you follow the equation, there is a sign ambiguity, right? In terms of the gamma. When gamma is expressed in terms of K is the K is expressed in terms of measurable quantities. When we say measurable quantity, so we all know that VNA can measure the S11 and S21, right? So these property we can measure, and finally we have to process it, and we need to get the property of epsilon and mu. Okay, this is our final goal. So measurement can be done on VNA by port 1 and port 2, as you can see in the picture. When we connect the VNA signal, then we can get the S11 and S21, the 2-port parameter, and then we can process it. But how mathematical equation can be processed? What is the problem? So when we process it, you will see that the gamma has its logarithmic of a complex number. Okay, see the first equation in this PPT. So if we take like that, if we try to evaluate the gamma, which is the exponent term, we will get the natural logarithm of modulus of t, and then the phase constant j phi. And this phi, we all know this is a mathematical problem. So when this phi is pi, I mean the 180 degree in the degree, or in radian pi, so ambiguity comes. Okay, then the general order expression will be, you have to add the j 2 pi n term, and now this n we don't know. So even the Nicholson Ross we didn't know. Okay, this is the mathematical expression. If you see the right hand side, this colorful picture where the spiral space is going upward like a helical, this is the expression of what you will get of the gamma if t is a complex number. So this is called as branching. So we don't know, we don't have a prior information of which branch we are operating. And why it happens? Because when the sample thickness, the d was the sample thickness in the earlier slide. So when this d is lambda g by 2, okay, the half wavelength. So half wavelength means what? This is the in the phase, we can say this is the pi. Okay, 180 degree phase shift. So when the sample length is approximately lambda g by 2, the branching problem appears in this expression, and then you cannot find gamma. And if we cannot find gamma, then epsilon and mu, which is the last expression in this slide, cannot be known. So what, and you can see the this guy, the Filippo Costa, he has in 2017 just a very recent paper. In this, he showed that what is the actual problems. Okay, so lambda g by 2 resonance, you can see what would be the frequency. We can calculate if the d is 8 mm, epsilon r is 9. So can you tell anyone that what will be the frequency where lambda g by 2 resonance will appear? I think from the free space, this is the approximate calculation, what I'm telling you. like whatever the C divided by D is the length of sample, that will give you the lambda in free space. Then you divide by 2, so lambda by 2 in free space, and then you divide by under root square of epsilon r. So epsilon r under root square is 3. So if you calculate, it comes 6.25. But I'm telling you, this is approximate. This is the not taking consideration of the waveguide transmission line. Okay, we will see in the next slide what is the actual frequency. So my point here is to just let you know that this is the problem. Okay, so see now how this problem is severe here. So we all know that we have taken epsilon, which is 9, and we are getting 9, but how much? Up to 6.4 gigahertz, and there is the lambda g by 2. If you take the propagation constant, actual propagation constant inside waveguide, which we all know will be 2 pi by lambda g, so frequency where lambda g by 2 appears, it will be 6.4. And from the simulation and experiment, he showed that here now you see the epsilon r after 6.4 gigahertz is absurd. I mean, it is not correct. But before it, when n is equal to 0, index is n is equal to 0. And also similar, it came in the mu r. Okay, you can see in the next graph on the top row. So epsilon r and mu r values are not correct after 6.4 gigahertz or even at 6.4 gigahertz. Even he don't know, so he tried to do the branch index n is equal to 1. You see the result, it is not anywhere good, it again went bad. So problem is knowing the exact branch index. So this is problem. So there are a lot of people doing in research. If you go to find the literature, you will find many researchers trying to solve it, and they are proposing different kind of methods, like iterative methods, like stepwise scheme. A lot of I don't remember even the names. You can find, I think, maybe 50 or 60 different very good papers. But the problem is still open. They have their own advantages and the disadvantages. So recently, our group has proposed one method. It is, I think, in May 2020. So it is a very recent paper from our group. So what we try to do, it's very simple. Not every problem has also solutions should be very complex. So complex problem may have a simple solution. It's not always obvious that okay, complex problems would have complex solution. No, I don't think so. I don't believe in that. So we propose a very simple solution of this problem. So what is the solution? Solution is, if you see the right hand side picture where S parameters are there, measured and simulated, which agree with each other with a small variance in the scattering parameter of reflection coefficient. So I don't think it's a big mismatch. It's almost agreeing with the simulated and measured result. But look the pattern of the scattering parameter, the maxima and minima. And this is obvious. If you remember from the last slide, the Filippo and Costa, you see this slide, the scattering parameter, the amplitude you can see. There is also maxima in S21 and minima in S11. You can see the blue curve is minima, is S11, and this is in one cycle, and here is a broadband. So you can see the same thing in the broad scale. Okay, so it is not different. This is the pattern which you get. This is obvious. You will get. So you will be ready for getting this. You know this. So what next you have to find? What information you want to extract from this a very unique pattern, and I'm saying you that by observing this, we try to give the branch index formula. So how it is a little bit of mathematics. If you if you agree with me, to process the mathematics, I can tell you. It is very simple. So if the transmission line parameter we see, and we observe the maxima and minima of S11 and S21, then we can formulate that what would be the S21 and S11 at those frequency. Just forget, people are trying to get evaluate the property at each frequency, but we are trying at the particular maxima and minima. Okay, so at particular minima and maxima, in when it is S11 is minimum and S21 is maximum. So like I'm talking about between 1.5 to 2 gigahertz. There is S11 minima and S21 is maxima. So at that point, the expression of TL, okay, will look like the exponent of exponential of minus jm pi. Okay, and when the S11 is maximum, S21 is minimum. Okay, so I am talking about the next point, adjacent point. So then the expression will look like this. When we know that already that how this expression is, and m is here not the branch, we will calculate the branch index from this m. So basic formula, basic term is to know the m value, and we know if it is a S21 will be -1, m will be 1 or 3 and 5. If S21 is 1, then 0, 2 or 4. So -1 and 1, you know what I mean. I mean, of course, in magnitude, always you will see the 1 or 0, but you have to see the phase. Okay. So if phase is pi, then you will get, okay, -1. If phase is 0, then okay, you will get 1. So phase is important, but we don't require also this phase information. So I will talk in the next slide. So here for your clarification, we also plotted the phase, which is in the blue line, dotted blue line is the phase of S21, and sorry, S11, amplitude of S11 and phase of S21 are plotted in the same graph. You can see only single graph in this PPT. And from this, we concluded a few points to remember to get this value of m. What we propose that the change in branch index can take place only at odd value of m. What is the odd value of m? Like m equal to 1, you can see there is a change. Then m equal to 3, there is a change. In between, there is no change in m, while m is changing each time. Okay, so if we say that the frequency point related with the minimum is f2 and maximum at f3, then we can know the f2 and f3 formula by processing the earlier formula, which in the last slide. And then by this knowing this f2 and f3, which is measurable by just getting the S11 data and magnitude data, we don't even require the phase data. Just phase is given for just simplicity to see, okay, this is happening there. So we can know what is the index value n in terms of m, and m can be calculated from the floor value of this f2 and f3 frequency. Floor value, I think we all know that if you are getting 2.4, then you have to take 2. Of course, m should be integer, right? This is a common information. Okay, so I want to just conclude this TR technique here, because the problem was the n, finding problem of branch indexing, and we propose somehow this branch indexing value easily. Now going to the back to that problem, you can solve the equation, and people are doing NRW is quite established math. The problem is the finding branch index. I'm trying to now come to the waveguide technique, but this is resonant. Okay, previously was non-resonant, that was transmission reflection, where S11, S21 with magnitude and phase was required. Now we don't need this S11, S21 data. We just need the resonant frequency and quality factor. And then suppose this is a cavity, and you have to know what will be the material parameter. So you have to perturb the cavity. Okay, so this is quite, I'm talking very old book, means standard book problems. Okay, this is not very advanced. This is very old technique. Perturbation, cavity perturbation are quite studied since a long time. But the problem is how you will make a precise measurement, because you have to make some device which resonates at 2.4545 gigahertz. So if this is a requirement, how you can model this device? To know beforehand, you should know beforehand what is the material property. So, and it should be precise, not just 2. What is 2.14 or 145? So that accuracy in measurement, it would give you the better design perspective of any device. Filters, resonators, couplers, you take the name, and each of the devices are made of materials. So precise values of this measurement technique is known as also the resonant technique, cavity perturbation technique, where small amount of material is inserted in the cavity, and changes in this frequency and quality factor are noted and can be processed to get the information. So I think it's a common textbook problem. So this is just taken for the introduction. So okay, suppose we have a waveguide cavity, and we all know that this is the standing wave. So the standing wave will form, and it will look like this if you are talking about the seventh order mode, TE107. I think the audience is well aware about this electromagnetic field inside the cavity. So it will look like the wave will look like, electric field wave will look like this. And when we perturb it, like the last figure in this PPT, the material is placed in the center. So in the center, you can see there is a material, and in the graph, which is steady graph, you can see that how the black line is changed. So I want to show that that how the electric field changes in real. Okay, this is the inside story, and how we process this data. So that is the part that I will discuss after this slide. In this slide, I want to show you that how electric and magnetic fields are distributed when you excite a cavity. So what you have seen in earlier cavity, I have made a slice on the half or across the length. Okay, so if you make a slice on the length, half of the length of the cavity where the sample was placed, okay, if you remember exactly, so you can see the electric and magnetic field of TE104 and TE105. These two modes are taken purposefully. One is the even 4 and one is the odd 5. So you see the electric field EY and on the first row. Okay, so you see in the fourth mode, which is the even, I say even mode, it is different from the even mode what is known for the even mode. So I just use the terminology. So in even mode T104, you don't see any electric field on C by 2, half of the length. You don't see, right? If you agree. But in the T105, you see first row, concentrate on the first top row, you will see that, okay, there is electric field at the cross section where is the cut is made. So if we place a sample there, what we measure? We measure the dielectric constant, because that will directly associated with the change in electric field. Okay, but if you come down, the Hx and HX of T104 and T105, because we know that the rectangular cavity has only one mode, only one electric field component, Y component, but we have two components of magnetic field, HX and HZ. So I'm talking about now HX. So HX will be absent on the mid plane of this waveguide, the E plane, mid E plane. So there will be no interaction of the magnetic field of cavity with the sample if we place in the middle. Now come to the last row. There is a HZ, and HZ component also absent at the very center. Okay, not at the side. If you go on the side, there is HZ present, because HZ always appear across the side walls of the cavity. So, but at the center you see there is a blue, and blue means zero. There is no field. So if sample is very thin and placed in the y-axis, along y-axis, there is no interaction with the magnetic field, and only interaction will be, so whatever change you will see in the resonant frequency or quality factor would be resulted due to the perturbation of single component of electric field, that is y component of electric field. But in coming on the T104, if you put the same sample, what you will get? You will be perturbing the magnetic field. You see now the column wise, okay, first column. You will not perturb the EY, you will not perturb even the HZ, you will perturb only the HX. So this is the beauty, okay? This is the beauty of the electric and magnetic field of the waveguide. And by knowing this property, you can characterize the material. So I want to try to present you the simplest way of what is the processing technique, okay? So coming to now a little bit of calculation, because calculation will be always be there when you process the data. So we know all the electric and magnetic field, it is already available through the field theory of any advanced microwave book. And if you remember the first slide of this waveguide resonant technique, I tried to show you that what is the C, if you remember C. So if you put the value of EY and take the dimension of the sample, which is placed on the center of the cavity, then you will find this expression of C. It's a little bit large, but okay, this is mathematics, so you don't have to worry about that. So what if we try to make it as a complex permeability measurement? So then you have to place it along the width of the waveguide, okay, and then you again process and you will get the formula of permeability, okay. So these are 5 years back my research during my PhD. So, but you see these problem on these techniques, the two techniques which I represented in the resonant cavity, the samples are always a full length sample. When I say full length, means top to bottom, it is touching, you know, it is not like a small sample, or it is thin, small in volume maybe, but not small in length. It should touch top to bottom through the width or through the height, okay. So then this technique is valid. But you know, the problem is always open. As I said you that I tried to discuss the open problem. So problem is like when sample is now not touching the ends, because in material industry or material processing labs, even I came through 2 labs, so they have their usual preparation method. They mix some material, they try to amalgamate it, they try to process it, and they try to form it in a form of bar or pallets, mostly cylindrical. Not you will even get every time, you know, samples sometimes are very costly, you know, in nanogram. They purchase in nanogram. Samples are so much costly, some samples. So you cannot measure it in a bulk, okay, at first, because you don't want to spoil your money. You have a small size sample and you want to know the precise value of its property. So how you will get through the problem, and what will be the problem? If we do so, if we apply the earlier existed problem in the same approach, will we get the exact property of material? Will we try to sense the exact data? I don't think so. So we try to, it is published in January 2019. It's all quite a recent paper. So what we try to show here, that now problem will be little bit advanced, okay? And what will be the advance? We will talk about it. So when the sample size reduced, you see the second picture in the bottom. So this is a cross section of this wave, the cavity, and the sample is placed like that. So we know if it is a magnetic sample, so magnetic sample has its north and south pole, and the magnetic moment, the moment of this magnetic material will be directed across the x direction. Okay, we can say this is a polarization of the magnetic polarization. So this now is a problem of many faces. First is the, we all know the classical theory of image of reflection, right? So the boundary is PEC, and the chart, and this is the magnetic charges, you can say. It's not actually the actual representative of charge. Always the magnetic loop is present. So if north and south poles are there, and there is a PEC boundary after a certain length, so it will see an image also, right? So the theory of images will apply. The theory of this polarization and demagnetization factor will appear. What I wanted to say you, that the HI is the internal magnetic field. Okay, previously we were considering that whatever the HX, applied HX, is equal to the internal magnetic field of this sample. So whatever the field applied, it will be remain tangential and will remain same throughout the sample. We were assuming previously, but now because of this limited length of the sample, the polarity will develop. The charge bounded on the surface will appear at the end of the sample, and this charge, or you can say the poles, will create a new problem, which is the effective magnetic field inside the sample. So we can say this is like a, okay, HI equal to HX, applied magnetic field, plus HDX. HDX is the demagnetizing magnetic field. Okay, so of course it will be opposite, and it will oppose the applied field, so it will be negative in magnitude, but since it's a vector, we can write HX plus HDX, and HDX can be expressed in terms of demagnetizing factor NMX and the magnetic polarization vector M naught. Okay, so this is a quite classical physics. So our motto is to get the NMX, the demagnetizing factor. So don't worry about this lengthy expression on the top. This demagnetizing factor is really calculating this is really tough. Okay, this very good paper is there in the bottom. You can see published in 2002 by Chen and Pardo. And they try to figure it out by numerical methods, and we try to formulate in our way. So we got this, and then in the second image you can see what is actually happening. So the poles from the PC boundary, PC wall 1, you see PC wall 1, you see, and PC wall 2 also. So N pole, because of the PC, create another N pole on the same distance. And similarly, the S pole, because of the PC wall, has another S pole there. So please let me know before 5 minutes if I am. It is a request to the organizer. So if I am going, I mean, taking a long time, then please let me know before 5 minutes. So I will conclude the session. So how much time I have left?
Now nearly 3:30. You have got 15 minutes more, and after that, some 10-15 minutes for discussion. You can take 20 minutes. You can take.
Okay, thank you, sir.
Welcome.
So yeah, so I was telling that this is the multiple images problems, theory of images, and if infinite image will form because of the PC wall, two PC wall. Okay, so concluding this, because now we have to add this vector. Okay, we try to get the the net magnetic polarization vector Mn. Okay, so and Mn can be summarization of this. You can see the first formula on this PPT, and by knowing this Mn, we can know the HDX. You remember HDX was the depolarizing magnetic field, which was added with the HI, which was added with the HX, applied magnetic field, to know the actual internal magnetic field in the sample, and that is required before integrating and applying the cavity perturbation. So you can see in this graph on the right hand side where I have plotted this NMX and IMX and NTX. NTX is the total demagnetizing factor due to this small sample. And you can see in this, I will refer that actually I want to cover more good topics. So I will refer the viewers, if you are really interested, then you can go through this paper for detail. So I will try to, and then I will get some time to discuss more, because I have a lot of good things to tell you. So okay, in short, now you know HI, so you can process the this equation, second equation, and then you can get the value, the permeability value. Okay, so I just want to, sorry for, but if you can ask questions later if you have. So this is the real experiment which we done. You can see this is the magnetic sample inside the in rectangular cavity, and this sample, you can see this is not touching the end of the PEC wall, and we got this kind of result. So what I wanted to show here, that in three cases, three samples we have taken, and compare with the earlier presented technique and this advanced technique where the sample is small. So we got always better accuracy when sample is smaller in dimension. U by A represent the ratio of the sample to the waveguide width, and when it is 1, that means it's completely touching both the end, and when it is 0.1, it means very, very small, right? So you focus on the lower scale of these lower two graphs, which represent the error. So any technique will verify from the error how much error it is. So you can see error is very less when the sample is lower in dimension, and also if it is higher, then this method is giving almost very good accuracy. Okay, but earlier methods which I discussed in earlier way, where this sample were fully full length sample, then you can see that the error is still 0.5 or 5% maximum, but when the sample size gets reduced, you see that the error is very high, approximately 50% or 40% or 30%. But our method, in where this new method now accommodates earlier methods as well. So this is the proposition here. Coming to this I like this subject very much, so I want to talk to you today. So this is epsilon near zero sensing. So epsilon near zero, it comes under the metamaterial subject. This is not really not there's a practical practical material. Epsilon near zero is not found in nature, but we can emulate this condition as the metamaterials are emulated by making FSS kind of a unit cell and mimicking it on the large scale, and we can modify the propagation of electromagnetic wave because of the properties at each unit cell lattice is changing the wave accordingly, and it can behave like a imaginary where the propagation is negative also sometime in the backward direction it can process. So we can manipulate the electromagnetic wave by changing the medium property, and when it is epsilon is negative or mu is negative, then k will also be negative in terms of propagation constant. So but I am talking about a specific kind of metamaterial which is epsilon near zero, not negative and not very large value greater than 1, or I'm talking about nearly zero, fairly zero, 0.5, 0.01 kind of. So how we approach to this epsilon near zero type of material in real sense. So suppose we have a parallel plate waveguide, we can see in the left hand side, and then in the right hand side we are seeing the cross section, but we have added two more section where the sections are not equal in height. Okay, so D is not maintained. Somewhere is D, somewhere is H. So if we section 1, 2, 3, you can see, and if we try to write the reflection and transmission parameter from transmission line theory, it will look like these two expression R and T. You target on R. When R is 0, reflection is 0, we consider, okay, transmission will be maximum 1. So ideal case, when will be R0? When Z1, Z01, that is the impedance of section 1 will be impedance of section 2, because section of 1 and section 3 are identical, so their impedances will also be same. So if Z01 equal to Z02, then there will be R equal to 0 and T will be 1. Okay. And this condition will, if we try to solve it, you can see that what is the expression. This is the quasi TEM kind of wave we are talking, because in the parallel plate waveguide the TEM wave exists. Okay, so TEM wave, in this TEM we can see what will be the impedance of section 1, section 2 and section 3, and if we compare it, if we equal it, then we can know epsilon RH, the dielectric constant of this smaller section, will be the dielectric constant of the larger section epsilon RD times the ratio, the square of the ratio of the heights h by d. And this is quite beautiful expression which tells what it tells, that the dielectric constant of the lower section, lower height section, is dependent on the ratio of the heights. So if you get the h tends to 0, you say very, very less, then you can control whatever the permittivity of the epsilon RD, you can tune this effective permittivity of the lower section, right? So this is the way to get the epsilon near 0 kind of transmission line. Coming to the case B, rectangular waveguide. So I think the parallel plane waveguide is quite hard to excite, and in daily life it's quite complicated. So rectangular waveguide is very common. We read in every microwave syllabus. So rectangular waveguide, it is also can be done. How? Actually, this is quite dispersive, we all know. So if we write the expression of beta, where the cutoff wave number is this and the free space wave number is this, and mu and epsilon. So considering this, they're like a non-magnetic material, like it is filled with the air. Suppose it's air, non-magnetic, so it is mu r is 1. We can also write the transmission line approach beta, which is where the epsilon E is the epsilon effective, okay? And we just compare. So we can know the epsilon effective would be written like this. The rightmost uh, expression in the down of this PPT. So you can see on the bottom last expression where epsilon E is written, epsilon effective is written in terms of epsilon. Epsilon is the permittivity of actual permittivity of waveguide, whatever it is. If it is air, it's epsilon R is 1, or if it is not air, then it can be any finite real number, 2, 3, 2.4, whatever. But epsilon E depend on also on the other factor of Kc, the cutoff wave number. So we can know that coming to the very dominant mode. So dominant mode say, okay, m equal to 1 and n equal to 0. It made life simple. Epsilon effective can be written in simplest form this. And if any one of you try to just formulate in MATLAB, I wrote, I think, 10-line program. It's not very you just try to plot it. You will get, I plotted with the two, I mean epsilon R, I'm varying epsilon R, the real dielectric constant of this waveguide, and I'm changing it and plotting it over the frequency, and I'm plotting for fixed waveguide dimension. Suppose this is the WR90 waveguide. So I can see, oh wow, this is like a epsilon effective, which is plotted on the Y scale. It's changing, and there is a epsilon effective zero line. I draw the zero line. You can all see the zero line. So at each of the frequency, at a certain frequency, it will cross that. So that what it meaning that? It means that at that frequency, the waveguide effective permittivity will behave like a zero effective permittivity. And near about that frequency, it will behave as a epsilon near zero waveguide. You agree? Similarly, if you just change the waveguide width A and just fix the dielectric property, don't change the dielectric property, you will see the similar expression that at one time at frequency scale, effective permittivity will cross the zero line. So I'm talking about that epsilon near zero kind of waveguide, and we know this is again the very fundamental, but I have written in this book chapter. So that I want to tell you that this is a now we know that, okay, if we control the waveguide height, we can try to approach the epsilon near zero, and you can tune the this frequency of epsilon near zero by changing the waveguide width. So here I want to present you that how scattering parameter can be written in terms of this T matrix, the T network. And if we know the T network parameter of impedances, then we can write the S parameter also of the any waveguide. Okay. So in the lower row, you can see I have reduced the width or height of this waveguide. And this is the problem of small capacitive window, and this Marquis has explained it in very well. This is not my expression. You can consult the Marquis book, Waveguide Handbook, and this is very well explained there. Just I try to formulate it in terms of it was written in terms of admittance, and I have tried to formulate pi matrix, and I have written in T matrix. So I change it with the impedance so that it can align anyone very simple way to the theory of impedance, and the transmission coefficient and reflection coefficient can be written. So you can write it and you can plot it. So I have plotted, and this plot see that the plot says that for p equal to 0, p equal to 1, and p equal to 2, what is the p? P is the TE10P mode. Okay, so you see that if we increase the length of the waveguide section L, which is the short height, and length we increase the length, each of this p greater than 1, p greater than 0 shifts along the frequency scale, but p equal to 0 is every time at the same frequency with the same amplitude, and it is not changing. And if you know anything about quality factor, you will see the graph and you will say that quality factor is very, very high for p equal to 0, because the half bandwidth is very small compared to the p equal to 1, 2, and 3, right? You agree? And in the lower section, lower picture, you see I have plotted the from HFSS we simulated it. You can also simulate and you can see the electric field intensity. You see the mind-blowing electric field intensity. It's a very, very high intense electric field in the channel in the lower section compared to the other waveguide launcher section. So what is actually happening? It is not a miracle. It's a power. It's a problem of the power equilibrium. Okay, like the power expression, if you remember, it has the B expression, the expression of height. So if you reduce the height to deliver the same amount of power, electric field must be intensified in this channel in the lower height compared to the other larger height section. So for the sensing application, now it becomes very important. Why? Because electric field intensity is very high and it is not changing. It is not, phase is not changing. You see the beauty of this. The phase is not changing. Phase is almost constant. So I have just calculated numerically how the electric field, how much the strength is increasing across the length and across the width. So you can see it almost 10 times because I have chosen the ratio 10, height ratio 10. And okay, and this is the first paper from very good group, Andrea Alu and Ann Ingeta from Penn State, I think USA. So they have in 2008 they had first sensed the material which is in the yellow strip. If you can see in the lower left side picture, that that is the material placed in the ENG section, Epsilon ER0 section of waveguide, and they showed experimentally also that how the scattering transmission coefficient changes, shifts. The first group of transmission line is related with p equal to 0. So it is changing. You see, it is changing by just changing a small amount of epsilon cav. Epsilon cav is the permittivity of the sample. So it can sense. That is the motto. What we tried in 2015, we tried to come with the SIW technique. Okay, surface integrated waveguide, and this is fully laminated technique. So you can also try to practice it. You laminate it fully by the photolithography or just conductive plating. Here, what we did, the approach earlier was changing the epsilon cav, and then you shift the resonant frequency or tunneling frequency. Here what we did, that you also know that when we shift the width, we control the width and we control the frequency. In the second picture you can see that frequency is controlled. I mean TE10 is now approaching to TE20. Okay, and this is the also the beauty, that you can take this advantage to make a multi-frequency sensor. So what we have did it like, yeah, here you can see there is a two-layer structure. Each layer is not talking to each other, but coupled in with the coaxial probe on each of the side. And on the right hand side of the top row, you can see that how electric field are in the cross section of this structure, two-layer structure. So there are two-layer structures. So two separate tunneling frequency will be there. And can you tell which mode is this by seeing the electric field pattern? This mode is, of course, varying in the across the x direction. So TE1, that is for sure. And what about Y and G? Y is 0. And what about G? And G direction also, you see in the tunnel, there is no variation in the G direction. So it is also 0. So this mode is T1, 0, 0. And we place the center, the sample on the center, and you can see how the sensitivity of this sensor in the lower graph. Okay, so I want to tell you what I'm doing now, okay, and what is the recent work what I am involved and my team here involved. So this is recent work. It will publish in 2020. Now you can also find in the IEEE Explore. So this is a very well reputed journal in IEEE. We try to do here to give a solution to detect the rotation and proximity. What we are trying here, that making a microwave sensor, low cost sensor, which can detect physical quantities, like I presented in the introduction, like rotation, maybe the direction, like the velocity, maybe the pressure, maybe the temperature. You name it, and you can model, you can design it. You try to. This is the current research in microwave sensor, which is booming right now. So if you are planning to make it a research in sensor, I will welcome you to choose a practical sensor, practical physical sensor to design, which can sense the physical quantities like a torque, force, pressure, whatever you name it. So this is our sensor here designed. It's a very, very simple sensor. I always believe in simplicity. So, but taking two course of action, it detect the rotation, also it detect the proximity. So this is a CSRR called as the complementary split ring resonator. This you can see in the slide that this is the circuit diagram or equivalent circuit diagram of CSRR. So when you rotate this CSRR, what happens? This actually changing the coupling, not only the capacity but also the inductive coupling. So if I get more time someday, I will go in detail, but I don't think it will possible today. So this will change it, okay? And if we change the rotation, change the proximity, then the equivalent circuit on the right hand side, you can see the additional capacitance will develop. So we try here in this paper to give it is written into the designer perspective. So one designer can know the parameter and can design a rotation and proximity sensor. This is another very recent paper from our group here at Polytechnic Dance. So it is also a rotation sensor, but it detects direction as well. Okay, whether it is rotating right clockwise or anti-clockwise. So it actually based on the asymmetry principle. If it is asymmetric, then by knowing the phase angle, or difference in the phase angle, we can see how the sensor is rotating in which direction. Okay. And this is a very, very recent work. As you already know now that epsilon near zero, how it works. So another new type of device, which is mu near zero. It is the first paper, I think, as I remember, and I searched a lot in literature. So this is the first mu near zero type microwave sensor. It is published in Nature Scientific Report just now. And we have proposed the third picture in the right-hand side. This is our proposition. This is the proposed design, two-layer design. And it works very well with the mu near zero type of sensor. And this is the state of art which I done in the Prague in the when I was the postdoctoral. So this is a wireless scheme of sensing, which I told you earlier also, that wireless sensors are common based on the RFID principle. So it works in near field of this antenna. And now this central antenna system where the sensor is also located, as you can see, that the problem was to make it wireless so that it can be placed inside the jar or some environment, and we can sense from outside without any touch, without any, I mean, non-contact sensing. So and the problem was to detect the biological sample. So we figured it out, and we proposed this idea. Okay. So I want to advertise. I will take the advantage if my organizer wish that here we have open position of microwave filter, and I invite you that if you are really good and you are really accept the challenge in microwave filter and passive devices, you have a good grasp, and then this university will provide you a good opportunity, and this is very good group. So okay, your questions are welcome. I hope I don't spoil the much time. So okay, I will welcome the questions.
Hello, can you hear me?
Yes, I can hear you.
Okay. So first of all, thank you very much, Abhishek. Thank you very much on behalf of us, the organizers, the Department of Physics, and also from the attendees. So, dear attendees or participants, if you have any question, please type it. Yeah, yes, there is a question, I think. Okay. There is a question from Mr. Dr. Somanath. How the thermal gun is detecting our body temperature?
Yeah, it's basically, I think it's infrared signal. So it is commonly detected, that known for the detecting the temperature. So I think this is the answer.
Once again, if you have any more question, we are now open, and just type your question in the Q&A because there is some problem. If I could not let you speak, I'm trying, but I'm not. If somebody wants to ask a question, please raise your hand. Let us try once again. Please raise your hand. Okay, there is a question from Dr. Pramila. I'm just changing you. I'm allowing you to talk. You just try there. I think the bandwidth requirement in this platform is much higher, so it's becoming. Or Dr. Pramila, can you please type the question like before? That will be, I think, more time saving because we are nearing the end. It was a long day, so. I'm trying. I've already tried, but it's circling. So I think it will take time. It is not
And
permitting.
I can see only it's round,
Yeah, yeah,
it's
yeah, yeah.
waiting.
It's going like that.
You
Going.
can type your question maybe.
Yes, yes. You can, Dr. Pramila, you can type your question and retype your question. If there is any problem, you can clarify on that. That would be better, I think. Okay. Okay. Dr. Pramila has her question. Sir, I would like to know whether we can have microwave absorption studies using network analyzer.
Dr. Pramila, I will answer this question like, you can use the network analyzer to study your microwave absorption properties. Network analyzer only give the measured parameter like scattering coefficients. Okay, that's parameter, well-known parameter. But later you have to process and what kind of technique you are using, that is mostly important in this subject, and what is the algorithm you are using in microwave absorption. So yes, of course, my network analyzer is helpful in this study, but the associated the components are also required, and the processing algorithm should be well known. Yeah.
Okay, now we have got enough time, some 5 minutes more. So
Mhm.
you can ask question. The floor is open for your question for the attendees. If you have any question, any type of question, please throw it. And Abhishek is there, I think, to uh, take the
Yes,
question.
yes, I'm here, no problem.
Okay, okay. Uh, okay, another question. I think it has come up. Uh, Once again, Dr. Pramila, she has thanked you, and I would like to approach you regarding this. Thank you very much. So, obviously, I would request Dr. Jha to send the copy of the presentation as much as possible to us, so that what we have planned, that we will upload all the presentations in one Google Drive and share it to all the participants. And obviously, the video of the lecture would be uploaded in the AICT website after completion. And I think hopefully by tomorrow we will get, already I got a presentation from other presenters. I will start uploading into the Google Drive and sharing with you. Okay. And please, Abhishek, please give me the links for the positions of what you suggested here, so that we can circulate it among us different groups, so that the best deserving candidate can get this, at least try for this opportunity.
Sure, it will be my pleasure because we are searching the right candidate,
Mhm.
and still we have 3 weeks left to make the first screening.
Okay.
So if anyone try to apply before this 3 week time, so they will be considered on the first screening.
Okay, that will be fine. That will be fine. You just share it with me. Probably in your LinkedIn, I have seen, but if you send me the direct one, I can post across the groups.
Sure,
Uh,
sure. I will give you the mail. Yeah.
Okay, so if there is no more question, we waited. So once again, on behalf of all of us here together, we convey our sincere thanks and gratitude to Dr. Jha for taking up his time to be present for our all the attendees. Please, thank you very much. And